Okay, I guess it's recording. Yep. And then where is share my screen? Sorry, I'm not very tech savvy with these things. Oh, there it is, share. Share. Can someone either post in the chat or unmute themselves and say that they can see my screen with the paper on it? Because
Looks good.
okay, cool. Welcome everyone. And today's paper is called Discovering Faster Matrix Multiplication Algorithms with Reinforcement Learning. This is a paper that came out from DeepMind, and it's really interesting because they were able to find faster algorithms for doing matrix multiplication than what's considered state-of-the-art algorithms, and some of these algorithms have stood the test of time for the last 50 years. So I thought it was really interesting. There's a lot of really interesting things about this. And before I jump into to me about this paper, before I jump into the methods in this paper, I wanted to have one clarification, just because it confused me for a while, and so hopefully it will help other people if you had this confusion too. And then just one editorial about something I thought was really interesting. So the clarification is a lot of this paper is talking about the rank of 3D tensors. Rank is a term for tensors that's often used to describe, is also used to describe which something that's called it's like order or rank. So for example, a tensor of rank 1 is a vector. A tensor of rank 0 is a scalar. A tensor of rank 2 is a matrix. A tensor of rank 3 is well, then we start calling them tensors. Usually they don't have a name. That's one use of the word rank, and also the other word that they use for that is order. Here, rank of a tensor is something different. So if you're used to using that word to describe the order of a tensor, it could be confusing reading this paper. Here, rank is used in a very similar way that it's used for matrices. In fact, like I think from an intuitive sense, it's good to think of rank as the same thing as for a matrix, as for a 3D tensor, where it's the number of essentially rank 1 tensors that you have to, well, it's a combination of 3 rank 1 tensors that you have to add together to create the tensor you're talking about. And we'll go into more detail about what that means, because that's not a great explanation. But I just wanted to start off with that clarification. Rank here is like very similar to the idea of like rank in a matrix. Like what's the minimum number of vectors that are required in order to describe like the basis of a matrix? It's similar here. So one thing that I thought was really interesting about this paper is, I don't know about you, but there's certain elements of machine learning that I feel have been explored to death. And one of them is like basic linear algebra. And I think sometimes I think that's actually a bias, and like it's definitely a personal bias of mine. And I really feel like this paper is like challenges those types of biases, because like you think to yourself that everything under the sun has been studied for in linear algebra forever, and there's no room for improvement. And then this paper comes out and it shows that there's actually like a massive amount of of material that we haven't looked into. One is finding more efficient algorithms for calculating matrix multiplication, but another implication of this paper is that they find many different solutions to matrix multiplication, like algorithms for matrix multiplication that are equivalent in terms of the number of computations they require, but different from each other in a way where you can't I think you can't like linearly transform one into another. And so they said they've mentioned at the end of the paper that that's also a very interesting area to explore, because it could provide some like very interesting insights about the computational complexity of matrix multiplications in different types. So anyway, I just thought, this paper points out that it's like maybe we shouldn't have, or at least in my case, like I shouldn't have had that bias about how there's nothing left to explore in these things like basic linear algebra. And also just, I think one of the reasons why it's so effective is because this area has been explored so much, because they use so much of this like very strong structure in the problem to solve it with reinforcement learning and find all these new results. So anyway, let's jump straight into it. I think that I like to go through things in the way that I think of the paper. So I'll start with just a summary of what this paper was trying to do, and some of the, and that was like, they wanted to use reinforcement learning in order to find faster algorithms for computing matrix multiplications. They point out, and they actually have some results, which also show that you can, because this method is pretty general in terms of the training objective you use, and we can express multiple different training objectives essentially as rewards in reinforcement learning, that you can use it for other goals as well, like this algorithmic discovery algorithm, such as the one that they do is tuning to find an algorithm that works like faster on a specific piece of hardware. But they also mention other objectives you could use, like energy usage. So yeah, I think it's pretty generalizable, but they focus here on they design the reward function that they use in this paper around reducing the number of computations. So that's kind of like the idea behind it. And they focus on the paper is about matrix multiplication, but they actually point out later on that this can be applied to any bilinear operation. So where is it? It says, we'll go straight into like kind of what a bilinear operation is. It says algorithms as tensor decompositions. As matrix multiplication A, B is bilinear, that is linear in both arguments. It can be fully represented by a 3D tensor. So any this algorithm essentially applies to any bilinear problem. So another problem that they apply it to later in the paper is, I think, like multiplying a skew symmetric matrix by a vector, which is different than like multiplying two matrices. And they actually find like a provably state-of-the-art method for doing that as well in this paper, which is cool, by extrapolating out. We'll get to that later. But so this algorithm is for bilinear operations like matrix multiplication. And I wanted to really focus in on this diagram because like the really key part of this method is expressing a matrix multiplication as a 3D tensor. So I think in order to really understand that, like the paper, you need to understand what that is and what that means. So if you have, let's focus on the 2x2 case, and then hopefully my explanation is good enough that we can understand like the n by n, or the values that they use. Oh shoot. The values that they use over here are like, what is it? N by m by p. So n by m by p means you multiply an n by m matrix by an m by p matrix. But let's focus on the 2x2x2 case, which is what you see over here in A. So how is a 2x2 matrix multiplication expressed as a 3D tensor? Essentially, what the tensor is it's you take the input matrices, so like A and B, and for each input matrix, I mean, so you can see over here. So B is the, let's say, rows of the tensor. So B1, B2, B3, B4, and then the columns are the answer, C1, C2, C3, C4, and then the what would we call them? Like the depth. We'll call that the depth of the tensor is A1, A2, A3, A4. And so each combination of like B, so if you take a coordinate in this tensor, like let's say the one expressed by B1, C1, A1, that would be the value in that area, that tensor value would be 1. And the reason why it would be 1 is because it's actually expressing that we want to multiply B1 by A1. And the way that this this tensor expresses matrix multiplication is that it's saying that, okay, there's a 1 in this, if you can see, hopefully you can see my cursor in this one in this B1 times A1. And what you do is you multiply, like each place that there's a 1 in the tensor indicates a multiplication that has to happen to calculate the answer. And then you basically perform all those multiplications and sum. And so that's why, so for example, C1 is equal to A1 times B1, and then A2 times B2. And then you sum those two, so it's plus. So that's why you sum, like if you can see they're both in the same column. How much sense did that make? Does anyone have any questions, or like, I hope that made some sense. I think I didn't explain it super well, but I guess the key insight, if I'm trying to summarize it in a way that makes some sense, is that the way this tensor is not expressing is expressing a formula for matrix multiplication, and each place that there's a 1 in the formula indicates that there needs to be a multiplication at that point. And so if you sum all the 1s in this tensor, you get the number of multiplications that need to occur in the to calculate the resulting matrix. And one important point is that this 3D tensor, in the case of the 2x2 case, or any case, is agnostic to the values in A and B. So that's why they're using variables to express them. This tensor is the same. And
so does that mean that the M1 to M7 is like sort of like almost like an internal dimension of this product space, right?
Over here, where they're
yeah, or I mean the wherever these matrices are non-zero means they sort of flow into these M values, right?
So yeah, but I guess one thing that might be a little bit misleading is that the tensor in A is like U, V, and W in C here. If you multiply them together using the equation down here, which we'll go into in a second, equation 1, then you'll recover the tensor that's being expressed in A.
Yeah.
Yeah. So yeah, I guess you could say that they're the but the key point is that okay, the first point again is that so you can express any matrix multiplication as a formula in the form of a 3D tensor with 1s in it, and the number of 1s and 0s in it. And the number of 1s indicates the number of calculations, so and the number of multiplications, and that means essentially like the number of the computational complexity. Is that the right word? Sure. Like the number of computations you have to perform the matrix multiplication, the number of multiplications. And so if we can,
does that mean that the that multiplications are inherently more expensive than addition?
I guess so.
I have a question, actually.
Yeah.
Is this classical, as in like this tensor representation of matrix multiplication? Because I haven't seen this before, and is this sort of a thing that they do just? Is this just like in this paper, or has this been done like years ago?
Yeah. So so in B, they're referring to this thing called Strassen's algorithm, and the one interesting thing of like this algorithm was invented in 1969. It's considered state of the art, and it usually reduces the number of matrix multiplications that need to, the number of multiplications that need to occur by some number. So for example, in the 2x2 case, there needs to be how many, like 1, 2, 3, 4. I
Yeah,
forget.
I think yeah I remember for Stratton, like, but I think in his original paper, I don't know if he actually did this with this sort of tensor representation of the actual multiplication. Yeah, I don't know, because I haven't like seen it done this way before.
But I think
Well,
generally it's a fairly common thing, right? To have these tensor rank decompositions. I think at least in
I
physics,
guess, yeah.
because a lot of physical processes you sort of write as tensors, and it makes calculations a lot easier if you reduce them to only the necessary. So I think it's mostly used for symmetry matrices, like if you try to classify your atom orbitals according to what symmetries they have, you try to find out what is the tensor rank underneath that sort of represents that. It's really, really cool, but way above my head.
yeah, same. I spent I looked up a lot of stuff to understand this paper. But okay, so hopefully we've gotten the first key idea is that you can represent, sorry to keep repeating it, like you can represent matrix multiplication as a 3D tensor of ones and zeros, where the number of ones indicates the number of multiplications. But there's a next key insight here. So that tensor that I was just talking about, it's called, the notation that they use in the paper, it's called MathCal TN. And n in this case actually stands for n by n by n, which means that you're multiplying two matrices of size n by n. But you could also, this extends to any matrices of any size, so it could be n by m by p, but for, I think, conciseness, they're just, all the math is written in terms of n multiplying square matrices, essentially. So in this case, here they're defining in equation 1 the rank R of a tensor. And so these u, v, and w are vectors, or tensors of rank 1. And just like when you take two vectors of and this x with a circle around it, that's the outer product. When you take the outer product of two vectors, you get a square, well, depending on their size. If they're both the same size, you get a square matrix. If they're different sizes, you get some rectangular matrix. So here, u, v, and w are vectors, and when you take their outer product, you get a 3D tensor. Because the rank of the tensor is the number of combinations, like of u, v, and w, that are required in order to express the tensor T of n. So if we go back up here, you can see in C that U, big U, has 7 columns, and so does V, and so does W. And each of the columns expresses one of the, I'll call them rank elements. I don't think that's the right term for them. But so really the tensor over here that we're seeing in A is of rank 7, because you need 7 combinations of U, V, and W vectors, which are all expressed here, in order to recover to recover the 3D tensor you see in A. And the next key step is that the rank of a 3D tensor is equivalent to the minimum number of multiplications you need to perform in order to do the matrix multiplication that is being expressed by that 3D tensor. So just like I said before, that the number of ones in the tensor in A is the number of multiplications that need to be performed in order to calculate C, matrix C in A. Actually, that's I think the upper bound. The lower bound, like the minimum that you need to calculate, is the rank of A, of the tensor in A. And if you can calculate the rank, that means you have a formula for the minimum number of multiplications you need to perform in order to calculate it. So here's an example where you only have to perform 7. In B, you see you only have to perform 7 multiplications in order to calculate the values of C, which is the multiplications are M1 through M7.
Is there a priori some do you know whether there's some bounds? Because you know we get definitely 4 values out, right? C1 to C4. You would expect if it gets a bigger matrix, the number of the rank of the tensor must be growing, and probably growing faster, right? But do you know whether there are some kind of, I don't know, limits? You would expect a 5 by 5 matrix probably doesn't have a rank of 250 inside, right? It must be something of roughly the same order of the number of elements you try to calculate. It would be interesting.
I'm sure there's an upper bound. I don't know if there's like a lower bound that you can calculate, or like a tight lower bound. Because if there was, then we would at least know what we would have known that we had like hit the lower bound with
They're also not unique, right? Because you could always sort of rotate all of your rank tensors, and you would get another set of 7 orthogonal ones that are just as good, right?
Yeah, they actually do a lot of cool stuff like that as part of data augmentation.
Yeah.
But okay, so hopefully that all made sense. If it didn't, then it's a good time to stop and ask a question. So okay, I'll just stop for a second. Okay, with that in mind, they've kind of, with this whole explanation that I've been giving you, they've defined what their criteria or their objective function is for that they want to optimize for it with the optimization algorithm that they're using that they're solving with deep reinforcement learning. The optimization is to find the minimum rank expression of a tensor T, or mathcal T. And so they talk about how they use deep reinforcement learning for algorithm discovery in this case. So it's not algorithm discovery, it's for like bilinear problem solving discovery. So it's not all algorithms, but I mean, I'm sure you can find ways to generalize this. I don't know if you'll have as much structure that they take advantage of here, but maybe. So they describe how they turn the problem that we've just described into a game. And they call it tensor game. And they say in each step of the game T, the player selects a triplet. So they select a set of vectors, U, V, and W. And the tensor S of T is updated by subtracting this resulting rank 1 tensor from it. So they start out the game, as they say over here, with S naught is equal to, so the game starts to the original tensor. And each time they take away essentially they subtract what a rank 1 tensor from it, and they update it. And they say the goal of the player is to reach the 0 tensor. So all the values within the tensor is 0 by applying the smallest number of moves, because the smallest number of moves would be equivalent to like the minimum rank of that tensor. It says when the player reaches the 0 tensor, the sequence of selected factors satisfies the original equation 1. And they say to avoid playing unnecessarily long games, we limit the number of steps to a maximum value. So this is a like a reinforcement learning trick that they're using, because one of the key issues of reinforcement learning is that if you don't know how to play, or if you start with a really bad policy, or if you're working with a really bad policy, you can sometimes end up not learning at all. And in this case, there's actually the issue that if you continue to select like the wrong rank tensors, like the wrong U, V, and W, then you could infinitely go on in this game forever. You could have an infinite number of steps. So they just cut it at some point. And they say for every step taken, we provide a reward of -1 to encourage finding the shortest path. So you want to have the highest reward. So you want to have the lowest negative number. And it says, if the game terminates with a non-zero tensor, the agent receives an additional terminal reward equal to minus gamma S of R limit, which is an upper bound on the rank of the tensor. So they have some way of estimating the upper bound, which I think is probably pretty easy to do. I guess the upper bound of the tensor would just be like the number of non-zero values in it.
Sorry. As I understood, and sorry, my name is Joachim. As I
Mhm.
understood from this paper, upper bound, it's just sum of matrix ranks of slices of the tensor. So I suppose
you're right.
they just wanted to make it maybe less calculative expensive, and they just integrated with upper bound.
Yeah, you're right. They say that later on. For anyone who didn't get it, it's the way that they calculate the upper bound is they take each slice of the tensor, like the 3D tensor, so they get matrices, and then calculate the rank of each matrix, and then they just sum them. And they say, although this reward optimizes for rank and other reward schemes can be used to optimize other properties, they go through that later. It says, besides SR, and what I don't know why they put besides here, but that's just me reading this paper really carefully to understand it, because I thought it was like, this is not this isn't in opposition to the previous statement. But anyway, they point out that because they're trying to find exact matrix multiplication algorithms, they can constrain the values within U, V, and W to be from this set and that's true for standard arithmetic, that you can have -2, -1, 0, 1, and 2. And they say such discretization is common practice to avoid issues with the finite precision of floating point numbers, which everyone's probably, if you've worked with deep learning with neural networks, you usually come up with issues with that. Okay. So they say to play the tensor game, we propose alpha tensor, an agent based on alpha 0, which achieved tabula rasa, superhuman, which means like from scratch. It was like basically not trained to, they just initialized a random algorithm. They didn't like warm start it with a good algorithm. Superhuman performance in classical board games. So alpha tensor uses a deep neural network to guide a Monte Carlo tree search planning procedure. So I wanted to quickly go over what alpha tensor is doing, like kind of intuitively. I didn't want to go into too much detail, but essentially what happens is the model will output the model outputs two things, like a policy over actions and then a value estimate. And what Monte Carlo tree search does, they're using sampled Monte Carlo tree search, which is when when your action space is so big, you can't just like enumerate and choose all the options. So they literally sample options. So what they'll do is like at the first step, and this is a planning procedure. So you can think of it this as you have a policy over actions, which tells you like probably the likelihood that you should sample each action based on the value you think you'll get from that action. In this case, the value is the optimal sequence, like the number of steps in the optimal sequence from where you are to like terminating to getting the 0 tensor. So how many steps you still have to take. And so you start from where you're at, you sample actions, and then you go to a next state and you sample actions again. And in at each step, you're using, I'm going to zoom out a little bit now that you're using this equation here in order to choose which action to sample. I don't want to get into too much detail, but what this ends up doing is it gives you, you're sampling based on the perceived value that you're going to get from sampling that action, but also based on like how much you've explored it, because sometimes an algorithm, like the policy that you'll get is short-sighted in terms of which action it's prioritizing. So you want to explore to see if there's other actions which lead to better results. But the short version of what happens with Monte Carlo tree search, which is really cool, is you calculate a new policy based on the action counts that you have in your search, and that policy is just like a distribution over actions, and that's better than the policy that you had previously, because it's taking what you have to create the policy that you to calculate the new policy, which is a distribution over actions, and then you train your model to minimize the KL divergence between the calculated policy and the one that is outputted by the model by your model. If anyone had any, we can go into that a little bit later, but I actually think it's a really cool, really cool algorithm and way of training a model. One of the reasons being that it's not good to make massive changes in your policy from one step to the next, because then you can't reuse data in previous steps. Because your policy is so different that like the data that you have from previous steps is not useful anymore because it's essentially a different policy. But anyway, it allows you to make small incremental improvements, which is always good. But anyway, so it's a combination of using, in this case, a transformer, but a deep neural network and Monte Carlo tree search and a reinforcement learning objective, which is based on like maximizing the reward function that they use. Let's see. Yeah, and I guess one of the things that they point out is that instead of using actual Monte Carlo tree search, they use sampled Monte Carlo tree search, and that's because, as I say, we rely on sampling actions rather than enumerating them because the set of potential actions is this action space is massive for this problem. Okay, so I won't go through the neural network. It's interesting, but I think it's not like, it's more of like an implementation detail if you're actually going to get into this instead of like something that's really, the only thing that maybe they say is that they use a special kind of attention based on how they, I won't get into that, it's okay. But the algorithm, the network they use is interesting. And if I were to do work on grid data, I might like look into it a little bit more. So the first of the steps that they use is they use synthetic demonstrations. So they say, although tensor decomposition is NP hard, the inverse task of constructing the tensor from its rank 1 elements is elementary. So what they do as part of training their model is they calculate a ton of rank 1 tensors and then combine them to create different matrices, and 3D tensors, and then they have their some soup data that they supervised data which they can train their model on. And they say that we train the network on a mixture of supervised loss, which is, so they have these essentially trajectories of how you can add these tensors together to get a matrix. And so they can like reverse that to train a supervised loss and standard reinforcement learning loss. So then they also train using reinforcement learning, which is when the model is actually live generating trajectories and being trained based on its own exploration. And they say this mixed training strategy, training on the target tensor and random tensors, substantially outperforms each training strategy separately. This is despite randomly generating tensors having different properties from the target tensors. So that's the first thing that they do. They basically, at the same time as enabling exploration to find the best solution, they give like actual solutions to the model to train on. The second cool thing that they do is that they say the tensors is the tensor representing, MathCalT is the tensor representing the matrix multiplication by linear operation in the canonical basis. The same bilinear operation can be expressed in other bases, resulting in other tensors. These tensors are equivalent. They have the same rank, and decompositions obtained in a custom basis can be mapped to the canonical basis, hence obtaining a practical algorithm of the form in algorithm 1. So they say we leverage this observation by sampling random change of basis at the beginning of every game, applying it to MathCalT, and letting alpha tensor play the game in this basis. This crucial step injects diversity into the games played by the agent. So it seems like one of the things they stress in like throughout here, without I think explicitly saying we need this, is they needed to find ways to train the model on a diverse set of examples, I guess, to stop it from memorizing or something along those lines, because they first just showed us how they created a ton of synthetic examples that they train the model on, instead of just letting it explore and use reinforcement learning to find solutions. And then they also change the basis of the tensors that they're training it on so that they can have diversity in terms of the solutions that they're finding for essentially the same matrix multiplication. And they say,
How appropriate is the name? Sorry, how appropriate is the name game actually for this sort of setup? It feels that there is not much of a player-to-player interaction in that sense.
well, it's a one-player game, like solitaire. They define it as a one-player game.
Isn't that almost saying that like any regression algorithm is also a one-player game because you have an objective to maximize? So
Yeah.
it's cheeky.
Yeah, I think either they're doing it in order to like, maybe because it helps them create the comparison with AlphaGo, or maybe they have some people at DeepMind who have PhDs in game theory and feel like this is how they think about the problem. I'm not sure.
Yeah.
I'm sure they have people who have PhDs in game theory at
Must have.
DeepMind though.
Sorry.
And then they also have data augmentation, where they say for every game played, we extract additional tensor factorization pairs for the training network. Specifically, as factorizations are order invariant owing to the summation, we build an additional tensor factorization pair by swapping random actions with the last action for each finished game. So that means like every time they simulate a trajectory, they can actually just switch the actions that were chosen, like the order of the actions that were chosen, and create a new trajectory, which they can train the model on as well. So there's like a ton of data augmentation that's being done to take like a single matrix, like a single tensor decomposition, and make it into like, you could probably make it into hundreds or thousands or like so many.
Excuse me.
Yeah.
My name is Akin. I just wanted to, following the last comment, I just wondering, can we, okay, for me, reinforcement learning, and yeah, you're right, game theory really creates environment for such type of things like reinforcement learning. But can we say that reinforcement learning allows them to find new solutions when all these standard like regression methods, they just exploring what happened in the past? So based on what you have, you can develop something like concentrate one solution based on previous experience. In reinforcement learning, they try computer tries to find new solution, which wasn't available before, which is unknown before.
I think that's a very fair point. I think the fact that you sort of explore your sample space actively and sort of guidedly is what sets it apart from standard machine learning.
Yeah,
I think so, yeah.
Okay, thank you. Just maybe it's interesting point for discussion for future, because reinforcement learning is just different branch of machine learning. And for reason, usually you're right, it's more like game theoretical setup. Here, yeah, one player against the environment, but still there is some sort of the exploring, yeah. So maybe, okay, just anyway, we have good results, so it makes sense to reply.
I guess what I'm hearing from your point is that is reinforcement learning really finding a novel algorithm, or is it just found it through exploration, essentially, during its training? Is that what you're saying?
I want to say that, yeah, it's something new which we haven't observed before. So it means it's really learning something from own experience instead of based on what we give as a feed to this method, let's say this way. So
Yeah.
we don't like trying to find no, okay, like just okay, standard machine learning mostly like summarizing some experience. Reinforcement learning explores new ways of doing things.
We don't have like a data set that we exploit in less than we exploit runtime or computation time to get better performance, essentially.
I think that I hope I'm understanding your point, but one thing I will say is that I don't actually think that the point of this whole thing is that possibly that reinforcement learning can maybe find like is more intelligent or than humans in a way, because like at the beginning, they're just talking about how like reinforcement learning can more effectively search the space, given the fact that it's so much faster at doing exploration than we are. So it's like because computers can do computation faster, and we can parallelize it. We can create these like pretty good well, maybe not even pretty good, but like these exploration algorithms that are able to hone in on like good solutions. And so it's more of like the fact that we have the ability to use computers in this way, and that they can do this exploration in an effective manner, than possibly that they're more effective than us at finding solutions is, yeah. But anyway, maybe I misunderstood your point. I think I probably did, but if I didn't, and if I did, I apologize.
I just one thing, I think speaking about intelligence is more like philosophical thing.
Yeah.
But the fact is that in Go, as I know, AlphaGo really developed new strategies that people really try to learn and understand more efficient, as I know. At least I have read about it.
But I guess my point is that like AlphaGo is trained for like, I don't know how many, it's probably like hundreds of thousands or millions of years of wall clock time. I don't know how long, but so it's also like this algorithm has had so much more experience than a human could possibly have, because we can't live that long. But so we like, in terms of intelligence, I don't know how much you could call it intelligent, but it's the capabilities that we have with computers, and the fact that is what we're exploiting here. Anyway.
Okay, yeah, it's more philosophical, yeah.
He would argue the big breakthrough is actually, as you said earlier, the formulation by the researchers, right? They were really good at taking a problem that seems creative to some extent into something that can be methodically explored, and I think that is a big breakthrough in itself.
That's true, and then also that it also means that within this problem, there's some level of structure.
Yeah.
That's not random. You know, like if every solution to the problem is completely unrelated to another one, then there's no point in, like, reinforcement learning wouldn't get us anywhere. But the fact that there's some kind of shared structure between all these problems is what it's picking up on. And I think that's where they're saying, like, maybe we can figure out what this shared structure is.
That it might even mean something in terms of NP hard, right? So there might be problems that are NP hard, but sort of you can still find solutions reasonably well with methods like this that are explorative, and I wouldn't be surprised if there are some categorizations within that makes it harder or easier to exploit.
And so now we'll go into the results. So they apply, I guess one thing they apply their matrix multiplication to two forms of arithmetic, which is standard arithmetic and modular arithmetic. So modular arithmetic is like, so for example, our numbers that we count in are all modulo 10, is it 9? But anyway, when you get to 10, you just say 1, 0 instead of saying like you have another number afterwards. And basically that's what modular arithmetic is here. Like, so all of the experiments they do are in modulo 2. So they always have, all numbers are expressed as 0 and 1. Because if it's 2 or larger, then it's just you modulo it. But they show their results where they have like, if we look at figure 3 where my cursor is, you can see the best known rank, the one that's discovered by Alpha Tensor, and then the for both the modulo and standard case. So they seem to have like a improved more in finding like the better algorithms for doing matrix multiplication when you're doing it on, like, they call it a quotient ring, but like when you're doing modular arithmetic. Yeah, I was thinking the numbers would be like more different, but I guess it is pretty significant if you think that some of these matrix multiplications happen like millions of times a second throughout the world. So if you can reduce it by one computation, then they'll be a little bit faster.
I think a big point is also that, you know, we rarely ever multiply 2 by 2 matrices, right? But the way these work is they decompose into essentially chains of 2x2 multiplications, right? And so for a single multiplication, these savings sort of amortize over like a chain, and so that's where you get, I think, the bigger savings as well.
We call it a single recursive method. Yeah, you can multiply block matrices. So you can apply 2x2 when you apply this method again to blocks of 2x2 matrices and so on, recursive method. And you can save more calculations.
Exactly. Yeah.
So they just show that they're actually able to either find like an optimal solution based on, or no, they're able to achieve state of the art, or they're able to improve on state of the art on all of in all of the cases that they're showing, which is like these different size matrix multiplications. And then one of the things that do they say it over here? No, they say it over here, I guess. Okay. No. Okay, that's fine. Sorry, I've highlighted different things and I'm trying to make sure I see them all. So what the next thing they did is they wanted to point out that their method generalizes past just matrix multiplication. So they apply it to skew symmetric matrices multiplying a vector by a skew symmetric matrix. And what I think this is a really cool result is if you look at figure 4, you can see they're looking at skew symmetric matrices of different sizes. So this is n equals 3, this is n equals 4, this is n equals 5, and this is n equals 6. And they were able to extrapolate from there to n equals 10. And they say that they're actually able to prove that like the new algorithm that they found is it's more efficient at these larger matrix sizes. So they were able to like the alpha tensor found a pattern up to n equals 6, and they extrapolated. They noticed the pattern. I guess maybe the algorithm couldn't notice it, like the policy didn't notice it, but the people who were looking at the results noticed it and were able to find like a new algorithm which is provably better than what they had before. So in this way, it was like a tool for scientific discovery that had a human in the loop, but they were able to find like a provably better algorithm than what was there before. Yeah. And then the other result that they show is that they've shown here that they can apply to different types of bilinear problems. And then they also show that they can apply it to other use cases or training objectives. So the training objective that they train on is I'm looking at rapid tailored algorithm discovery, is that they want to find algorithms which take advantage of like the specific design of a piece of hardware. So in this case, if you look at they look at a specific type of GPU and a TPU, and they ask it to find optimal algorithms for matrix multiplication for both of them. And in both cases, they're able to improve on like what's the state of the art algorithm that's used right now, which is Strassen square. And also and by incorporating this in as well. And it's interesting because they say that there's like, I'll just read this part of it. They say, interestingly, alpha tensor finds algorithms which a larger number of additions compared to Strassen square, but the discovered algorithms generate individual operations that can be efficiently fused by the specific XLA grouping procedure, blah, 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 blah. So even though from a theoretical point of view, the algorithm that's discovered has more computation, requires more computation, it's more efficient on the hardware. So they show that it's actually able to find like these algorithms that are more efficient on the hardware that's being used. And just to finish it off, they say like some interesting further results for this paper is right now, the elements of the U, V, and W vector, if you remember them, they're fixed to be certain values. For like modulo arithmetic, all of their experiments were done in modulo 2, so they only had values 0 and 1 in it. And then in the case of standard arithmetic, it was from -1 to 2, just the integers from -2 to 2. And so they're saying like a potential additional element of this could be like actually discovering the factors instead of setting them. So that wouldn't be a hyperparameter of the method. And they say it'd be interesting to train these algorithms for things like numerical stability and energy usage, which sounds cool as well. I really like the one for energy usage. I was actually wondering how, because it seems like they found ways to reduce the amount of computation that needs to be done to perform matrix multiplication. So I thought, doesn't that reduce the energy usage? But maybe it doesn't. Or maybe there's, if you target it specifically, you can get better performance. So anyway, that's my long rant done on this paper. I wanted to leave at least a little bit of time for people to say their thoughts or say anything or ask questions. Yeah.
I have a question on. I wonder why they didn't do any sort of rounding error bounds for these algorithms. Because I remember like a sort of a big disadvantage for Strasson's method is that you sort of have a weak form of a rounding error bound. Like that's why sort of sometimes it's not good to use it as opposed to sort of conventional matrix multiplication, which gives you sort of component-wise rounding error bounds. So yeah, I don't know why they didn't go into that here, but I guess it was more focused on the deep learning side of things.
Yeah, it might have even just been that that's like a level of that might detract from the paper in terms of people understanding it and making it easy to read.
I guess, yeah, then you would become sort of a linear algebra paper than a machine learning paper. But there was one, I found a paper went on arXiv, I think like 2 weeks ago, about 2 or 3 weeks after this paper was published in Nature, which found a algorithm for 5x5 matrices, or found a scheme for 5x5 matrices that had one less multiplication than the method that they proposed in this paper.
Wow.
And they didn't use any machine learning. It was just sort of by hand computations of doing the sort of tensor representation of the multiplication, the matrix multiplication operation that they do here. So they use the same method, but they find sort of a better algorithm, I guess, than the one here. So that was sort of, I don't want to say like a rebuttal to this paper, but yeah, I guess the people in the linear algebra community, from what I've heard, aren't super happy that it sort of got such a big.
It might be like the one guy who beat AlphaGo once.
yeah, could be. Yeah.
But I mean, do we actually know whether this problem is itself NP hard? Or is it provably NP hard?
They say that finding low-ranked decompositions of 3D tensors is NP hard.
Yeah. Because the question is always like how good actually are stochastic mechanisms, right? Because this is ultimately a stochastic mechanism, and I think there are quite a few NP hard problems where the stochastic versions of them are actually not taking that much longer. You just are not guaranteed to get the best answer. And I wonder whether that plays in here as well, where you have a good chance of finding something that is good, and perhaps even the best, but it's at the end of the day, you don't know whether you are there yet, and I think that is the big caveat here. I wonder whether they can do the same thing with prime number decomposition, right? Finding ways of telling whether a number is prime or not. And I wouldn't be surprised if they could make some advances there, right? If you think about how there are these heuristics, like if all the digits sum up to something that is divisible by 3, it can't be a prime number, and so that they could build a machine that is very good at spotting these high level characteristics, which might make quantum computers sort of less useful than people thought it would be. That could have a big impact on the industry as well.
Yeah, it's interesting. Like I would have never thought. I mean, not that I'd expect. I'm not the bar for this, but I would never have thought about applying machine learning to this problem. So I think it's just super cool. Anything else I want to say before? No, I think that's it. Cool. Thanks everyone for coming, and hopefully we won't have to cancel the next in-person meeting because of tube strikes, and that we can meet in person.
That would be awesome. And we can go to the pub at some point. That would be nice.
Yeah, I know. Oh, I guess I don't know when we're going to announce it, but I think in early December we're going to do a paper club at the end of the day, so then we could go to the pub afterwards. We'll definitely announce it in a couple weeks if that ends up materializing, which would be cool. And it might be with another startup, so we'll be even an even larger group of people.
Ooh.
Great. Well, I'm going to
Okay.
stop sharing. Yeah, and thanks everyone for coming, and hopefully we'll see you here again next week.
Thank
Yeah,
you. Great
thanks for
talk.
the presentation.
Thank you for the presentation. Bye.
Thank you.
Thanks. Bye.
Bye.